Alright, I'm ready to show you some things with section 3.8, derivatives of exponential and logarithmic functions. Okay? It's a pretty straightforward section. It's not too crazy. Alright. The first thing is when you want to find the derivative of an exponential function, the derivative is really exactly the same thing. So it's a to the u. And then you have to multiply by the natural log of whatever the base is. So in this case, I have the base is a, so it's natural log of a. So it's that simple. It's the exact same thing times natural log of a. Then the chain rule always applies, and so you multiply by the derivative of whatever is in that spot there. So you multiply by du dx. So that's the derivative of any exponential function. In this case, a is any number, a constant of some sort. All right, positive number as well. All right, now if I do the same thing with e, then I would say, okay, then it'd be e to the u, and then I would say I've got to multiply by the natural log of whatever the base is, which is e, and then I multiply by the derivative of that function u, so du dx. Now, when you do e to the x, when you find the derivative of that, when you look at this is natural log of e, so we don't, that's equal to 1. So we don't really write that. So that's why when you do the derivative of e to something, it's always e to that same thing, and then times the derivative of the inside. So it's a little bit more simplified. So the derivative of e to the x is the only one where it's exactly the same as the original. All right, let's try an example. So this one, it says, y equals e to the x plus x squared. So finding the derivative, I would just say y equals, and I would rewrite this exactly the same. The derivative of e to something is that same thing. But then I have to multiply by the derivative of the inside. So the derivative of the inside is 1 plus 2x. And that would be okay. You can just leave it in that form. Alright? Alright, next problem, a little bit of an application here. So let's say we left some milk on the counter, not really a good idea. And let's say its temperature in Fahrenheit after t minutes is given by this particular function. It's an exponential function because we've got the variable there as an exponent. And we're going to answer several questions about this. So make sure you jot it down because I'm going to switch the slide for the questions. Okay, question number 1. What is the temperature of the fridge? That's kind of an interesting question. What in the world is the temperature of the fridge? So when you look back at the original, you remember that initially you just barely took it out of the fridge. I should say that. You just took it out of the fridge. So at 0 time, that's what you'd want to plug in. So if you were to plug in 0 for the t right there, that would all be 0. So let's see, maybe I show the work, maybe I don't. Let's see. If I plug in a 0 for this t, then this whole thing becomes 1. So maybe I do show a little work. So I'm going to say, use a different color here. So I would say y equals 72, and then minus 30, and I plug in the 0 there for the t, and this would end up being 72 minus, and of course that would be 30, because this equals 1. And so the temperature of the fridge then would be 42 degrees Fahrenheit. Okay. All right, so there's question 1, or A. B, what's the temperature of the room? That's kind of an interesting question too. What's the temperature of the room? Well, we know eventually the milk is going to reach that room temperature. So it really becomes a question of, hey, what's the limit as t approaches infinity? So here's a good application of, what in the world are limits good for? And also horizontal asymptote. Because remember that connection, the limit as x or t approaches infinity is the same as the horizontal asymptote. So if you look at the original problem, and if you were to graph it, Well, we know that typically the horizontal asymptote for these exponential functions is y equals 0, the x-axis, but this one is up, has a shift of 72 up. So that means that we could look at it and say that our horizontal asymptote is 72, and so therefore our answer to this problem is 72 degrees Fahrenheit. So graphically, you could sketch this. It starts off 0 temperature, or 0 time, it's at 42 degrees. And it basically goes something like this. And then it approaches, it only goes up. And it doesn't, actually this will probably reach 72 degrees eventually. It'll just equal 72 degrees. Okay? So you could graph it to figure that out. Maybe plug huge numbers in for the T and figure out the temperature of the rim. All right. When is the milk warming the fastest, do you think? Is it here, or is it earlier in the process, in the middle? What do you think? Well, let's see. I might even need to graph this to see if it even curves like this. It might even have a different shape to it. So I'll have to check that out in a second with my calculator. You correct me if it kind of actually goes a little more exponential and levels out. It probably does, actually. Let's see what I want to do. Oh, when's it warming the fastest? Well, it actually warms the fastest. It actually warms the fastest in the beginning. So it's the steepest, rate of change. And so it's right at the beginning. So let's just say at the beginning. Okay? All right. Next question. Determine algebraically when the milk reaches 55 degrees. Well, we know that the function equals, we know that the left-hand side is the temperature, the y. And so we can just set that equal to 55. And solve for t. So we're going to try to do that algebraically. So we have 55 equals, and that's 72 minus 30 times 0.98 t. So let's go ahead and subtract 72. So we get minus 17, and that's negative 30 times 0.98 raised to the t. And then I'm trying to isolate the t, so I'm going to divide both sides by negative 30. So 0.98 raised to the t, divide by negative 30. I got 0.56. So now I need to figure out a way to get the t. And what we do is every time we want to get the t down like that, or an exponent down, we usually take the log or natural log of both sides. So I'm going to go ahead and take the natural log of both sides. So that would be this here. The reason why we do that is because then we can use a logarithmic property that says that you can take exponents and you can put them out in front. So that's t natural log 0.98 equals natural log of 0.56. Then we can easily isolate the t by dividing both sides by natural log of 0.98. So t equals natural log 0.56 divided by natural log 0.98, and then that's something we can just plug into our calculator, and we get 28.7 minutes. Okay, so that's 28.7 minutes. We found out when the milk reaches 55 degrees. Last question about the milk, and then we're done with milk. Last question about the milk is, at what rate is the milk warming when the temperature is 55 degrees? How is the temperature kind of rising at that moment when the temperature is 55 degrees? Well, we go back and we go, well, we know when it's 55 degrees. We at least know it's 28.7 minutes. That's when it's at a temperature of 55 degrees. So how is it changing at that moment? Well, that sounds like the rate of change. That sounds like a derivative. So what we're going to do is we're going to find the derivative at 28.7. So we're going to say, and we're going to do this just with the calculator this time. We could do this, by hand, but we're going to go and use the calculator. And we're going to say y prime of 28.7 equals, or is approximately, and I'm going to show you how to use the calculator on this in just a second. So I'll wait on the answer. Yeah, maybe I'll just wait on the answer. So let's go to the calculator. Okay, so I have the function plugged in there, the one we were just working with. The x, as you know, are t, and so what I need to do is I need to figure out the derivative at, let's see, what was the derivative? The derivative at 28.7. So what I do is I kind of get out of this mode and I go math 8. Math 8 does the, and deriv. Mine's the old school, on the computer, but yours, figure out if you have a new operating system. It's still math 8. Then I'm going to go vars over to y vars. And I'm going to do y1. I got to choose that y1 and then comma x comma. So the x there is the derivative with respect to x, and then it's 28.7, and then I'm going to press enter. That gives me 0.339, which is approximately how much the temperature is rising at that time. So let's go back. So then we would just plug in we would say the answer is 0.339, and that's degrees Fahrenheit, and that's per minute. So that's the rate of change at that particular moment. Okay? So that's a lot with exponential. Let's take a look at a couple log things here. So we got a couple formula or a couple derivatives for logs. The derivative for natural log is slightly more simple. So derivative of natural log is just 1 over whatever's in this spot. So it's just 1 over that. And then, of course, the chain rule always applies. So I'm going to say it's multiplied by du dx. And then the log of a base other than e, this is just a log of base e. That's why we call it natural log. But if you have a log base of something other than an e, we say log base, whatever that is, then the derivative of that is the same. It's still going to be 1 over whatever's in this spot, but you have to multiply by natural log of a. So whatever the base is there, you have to also multiply by natural log of that base. And then the chain rule always applies. So we still have to always multiply by du dx if that's, if this is more complicated than just an x. So we gotta factor that in. All right. So we do one example of this type because the natural log is simple. It's just 1 over whatever's in that spot times the derivative of the function. Well, let's finish out with this example. So derivative of log base 7 of 4x cubed minus 2x. So it's still pretty easy. It's just 1 over whatever this is, whatever that junk is. You have to just do 1 over that. So 1 over 4x cubed minus 2x, and then again it's times natural log of whatever the base is there. And then chain rule always applies, so we multiply it by the derivative of the inside. So the derivative of the inside is 12x squared minus 2. And that's an okay answer, or you could just kind of make sure that that's on top. So however you want to clean it up is fine. So just, how to do that. All right, so I think that'll do it.